probability density. Okay, so we mentioned this earlier. Psi squared is the probability density. It's this wave function squared, gives us the probability of finding an electron in a particular unit volume. And we can calculate this probability density for different quantum numbers, and that gives us the shapes of these orbitals. So the s orbital is spherical, so that's kind of nice. S, sphere, they both, have s there. The probability density increases as the distance from, the probability density decreases as the distance from the nucleus increases. So when we look at these plots, we can think of them as resembling multiple exposure photographs, like I did with Andrews. Like, okay, you take a picture, where's the electron? And then 5 seconds later, you take another picture, where's the electron? It's important to remember that the electron is not fluttering around the nucleus like a moth around a flame. That's not what it's doing. In a sense, the electron's location is spread out over the entire volume of the orbital because it has this wave-like nature. So the multiple exposure would give us something like this, where we'd see that the probability of finding the electron is greatest near the nucleus. The probability of finding the electron over here is very, very small. So it's probability. And if we look at the graph, probability density as a function of radius, we see that the probability is highest at the nucleus. This isn't really very accurate because is the electron right at the nucleus? No, it is not. And so a plot like this is a bit misleading because it implies that most of the electrons are going to be found at the nucleus, and that's not correct. So they do something else with those functions, and they do the radial distribution function. That's the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. And this reminds me of the sorts of stuff they do in calculus, and they're cutting these thin layers and they're adding these things together and doing all these crazy things that mathematicians do. But the bottom line is this gives us a better picture of where the electron is likely to be found. So the total radial probability for at some distance from the nucleus, r, is equal to the probability per unit volume times the volume of the shell at that distance. So when you multiply these two functions together, you've got opposite trends in r. Psi squared has a maximum at the nucleus and decreases as r increases. The volume of a thin shell is 0 at the nucleus and increases as r increases. So if you think about a thin shell that's far away from the nucleus, its volume, even though it's thin, because now it's so much larger, the volume of it's going to be larger. And the result of all that is that we get a plot like this, which gives us a much better picture of the density of the electron probability. So here at the nucleus, the probability of finding the electron at the nucleus is 0. And it goes up very high. It hits a maximum, this is for hydrogen, at 52.9 picometers. And then it falls down after that. This 52.9 picometers is the same radius that Bohr predicted from his study with his model of the hydrogen atom. But it's a very different conceptual concept. That doesn't make any sense. There's a conceptual difference. So for Bohr was saying that the electron is always found at 52.9 picometers. That's the distance of its orbit from the nucleus. It's like it's tied on a string, and it's just going around in circles around the nucleus. That's what the Bohr model said. But quantum mechanics says the electron is found at various radii, various distances from the nucleus, but 52.9 picometers is the most probable distance. Okay? So there's a conceptual difference here. But 52.9 picometers is the most probable distance that you would find an electron at. The 2s and 3s orbitals are also spherical. S tells us the shape of the orbital. S is spherical. The 2s orbital is larger than the 1s, and the 3s is larger than the 2s. As the principal quantum number increases, as n goes from 1 to 2 to 3, the orbitals get larger, and thus the average distance, or the most likely distance from the nucleus, gets larger as well. 2s, 3s orbitals contain at least one node. What is a node? Okay, a node is where a wave function goes through 0. One way to think about these orbitals is that they're basically like standing waves. So, I don't know if you've ever done this experiment. If you get two people holding a rope or a string and you shake it just right, you can get a standing wave set up where the rope is going up and down and up and down, but there are points where the rope isn't moving at all. And it's a standing wave. Guitar strings, the waves are too small for you to be able to see. I should probably look for a video. I'm sure I could find a YouTube video on this. But a guitar string will set up standing waves, and that's where we get the tone from. So an orbital is a bit like a standing wave. The 3s and 2s orbitals are going to have at least one node. A node is where the probability is 0. The electron will not be found at the node. It'll be found in one of the other regions. And this, I think, conceptually is helpful too, because we can see this standing wave, and yet do we really know exactly where the rope is? No, we don't. If we take a picture of it, now we can see where the rope is, but we don't know what the wave is doing. If that helps. So if we look at the 2s and 3s orbitals, here are their distributions, and we see that there's a node at the nucleus, like with the 1s, but there's also a node over here. And then the maximum probability is here. The 3s orbital has 3 nodes, one at the nucleus and then 2 others. And so if we look at a cross section of here, there's this region in here where you're probably not going to find the electron. And this one has a couple of little stripes. It's a little bit, it almost looks like one of those everlasting gobstoppers. You know, and you lick through the outer layer and it changes color and flavor, and you go through the layers like that. If we draw a surface, usually what they do is they enclose the 90%. So this would represent 90% of the time the electron would be within this sphere. And these are a lot easier to draw than the fuzzy dot ones. But don't get, don't lose sight of the fact that it is not this simplistic. This is not a container that contains the electron. Okay? This is just the region in which the electron probably is, but it could be outside of that. It is also not just zinging along on the surface of this. It's kind of everywhere and nowhere at the same time. Anyway, principal energy level, each one has one s orbital. And it is the lowest energy orbital in a principal energy state. In my crazy hotel, usually you don't want to have a hotel room that's right by the elevator, because people come up late at night and they're loud and they're walking past your room. If you're at the far end of the hall, nobody's walking past your room. So the s orbital is closest to the elevator. The s orbital room is cheaper because it's less desirable. The s orbital in any principal energy level is going to be the lowest energy level. It's going to be spherical, and it's going to have nodes, and the number of nodes is equal to n minus 1. P orbitals. The first energy level, n equals 1, doesn't have a p orbital. It only has an s orbital. But the second energy level and above all have p orbitals. And as we noted earlier, the p orbitals, there's going to be 3 of them with the magnetic quantum numbers minus 1, 0, and plus 1. They're each going to point along a different axis. So we've got x, y, and z. They're two-lobed, and they have a node at the nucleus, and then a total of n other nodes. So they look like this. This is the most accurate, more of a multiple exposure picture. So these fuzzy regions of probability. This is how we typically draw them. They kind of look like balloons. And so the px orbital is going to have these 2 lobes lined up along the x-axis. And the py orbital is going to be perpendicular to that. And the z orbital is going to be up and down, perpendicular to both. So you've got these 3 objects, and they're all perpendicular to each other. You can do that with 3 objects in 3-dimensional space. The 2 p orbitals, they have a node at 0, but they don't have any other nodes. Here's our radial distribution function. Now, the electron could be in either side, and in a way, it's in both sides. Isn't that just lovely? Then there's the d orbitals. So as we go up, all the possibilities become greater. So above n equals 2, we've got the 5 d orbitals, and there's the quantum numbers for that. So 4 of these are aligned in different planes, and the 5th is aligned along the z-axis. Most of these guys are 4-lobed, and one is 2-lobed with a toroid. And these have planar nodes. The higher principal levels also have spherical nodes. You're like, what? We're just kind of putting this out there so that, yeah, these exist, kind of deal. Look at those guys. They're crazy. Okay, so these aren't as hard to understand. This looks like a doubling of the p orbitals, right? And so we've got one in the YZ plane and one in the XZ plane. So this is vertical, and this one's horizontal, and this one's horizontal the other way, and then this guy, that's vertical. This one's horizontal, and he's not lined up with this one. And then there's this guy. And we're not making these shapes up, okay? These shapes come from the complicated equations, okay? They're mathematically derived, and if you're interested in that sort of thing, you can take classes in that, and it'll all be very fascinating to you. And if you're not interested, you can probably live out your life quite happily without going any further than this. But those are the d orbitals. There's 5 of them. They don't overlap with each other, really. They're arranged around the same nucleus, but they're taking up different areas of space. Then there are the f orbitals. L equals 3, so now we have 7 d orbitals. Most of these are 8-lobed. Some are 2-lobed with a toroid, like that one wacky d orbital. And these also have planar nodes, and again, the higher levels have spherical nodes inside of them. Yeah, right? It looks like a balloon artist clown went nuts or something, lost his mind. These guys, I think, are particularly trippy. Those 2 right there. Yeah, what the heck? Yeah, there they are. Those are f orbitals. I don't have anything else to say about them. So these orbitals are determined by math. It's a mathematical wave function. So wave functions can have a positive or a negative value. And it can also have nodes where the wave function is equal to 0. So when the sign, we call the sign its phase. So if it can have a positive phase or a negative phase. And when these orbitals interact, because they are wave functions, they can have constructive or destructive interference. If they are in phase, if they have the same sign, they will become larger, and if they are out of phase, opposite in sign, they will become smaller. And we're going to look more at this in a later chapter. So here's an s orbital, and an s orbital being spherical, on the outside you're only going to see one of its phases. Here's a p orbital. In p orbitals, one phase is positive and one phase is negative. And if you look at the standing wave, remember these have a node here, one side is positive, one side is negative. And so then they can interact with each other, and they can either reinforce or destroy each other. And we'll come back to that later. So with all these crazy shapes, why are atoms spherical? Well, if you superimpose them all on top of each other, you get something like this. And the more orbitals you include in there, the more smooth the surface would appear. When you put all those orbitals together, the shape is going to be roughly spherical because they are arranged symmetrically around that nucleus.